Hi there, it's Yan again. Previously, we have used a frequency distribution, mean, median, and mode to describe and summarize data. In this chapter, we'll learn to summarize data by describing its variability. Variability is a quantitative measure of the degree to which scores in a distribution are spread out or clustered together. Its value ranges from 0 to positive infinity. It tells us how far the scores vary from the mean, how scores vary in general, and how accurately the mean describes the distribution. Now let's look at the example. Which data set is more spread out, and which one is more clustered together? The left one is more spread out, and the right one is more clustered together in this area. The simplest way to describe the variability of a data set is to identify the range of scores in the distribution. The range is the difference between the largest value and the smallest value. In this calculation, we only use two numbers, the largest one and the smallest one. In Chapter 2 of frequency distribution, we mentioned the real range, and the way to compute real range is the largest value minus the smallest one plus 1. Now let's look at this example. We have a data set of 5 numbers, 1, 2, 3, 4, and 5. And the range should be 5 minus 1, and it's 4. If I'm asking you to compute the real range should be 4 plus 1, and it's 5. Here's another example. Another data set of 5 numbers, 2, 4, 6, 8, and 100. And the range is 100 minus 2, and it's 98. Now, what is the problem here? The range of 98 is misleading because the extremely large number 100 makes the range large. But majority of the data set are smaller than 10. Therefore, 98 is not a good measure of variability for this data set. This tells us when there are outliers, range is not a good choice to measure the variability. To solve the outlier problem, we compute an interquartile range. Before we learn how to compute it, we need to introduce a fractile. Fractile is a measure that divides data set into 2 or more equal parts. Median is the score in the middle of a data set, so it splits data into half. Percentile splits data into 100 equal parts. And quartiles splits data into 4 equal parts, each containing 25% of the data. From the first quartile, the second quartile, the third quartile, and the fourth quartile. We'll use an example to compute an interquartile range and a semi-interquartile range. A researcher records the time in seconds that 14 customers waited in line to be served after ordering their meal. The times are listed in numeric order in this table, and there are 14 scores in this data set. First, we look for the median of the data set. There are 14 scores, so the 2 middle scores are 85 and 87. The median is the average of 85 and 87. It's 86. Now the data is split into half. We look for the median of the lower 50% of the data, which is 76. 76 is in the middle of the first 7 scores. And 92 is in the middle of the other 7 scores. So now the 3 numbers of 76, 86, and 92, split the data set into 4 equal quartiles. Inner quartile range is the range of scores between the first quartile and the third quartile. So 92 minus 76 is 16. So we can see inner quartile range eliminates the bottom 25% of the data and the top 25% of the data, because it's the range between the first quartile and the third quartile. Semi-inner quartile range measures half the distance between the cutoffs for the first quartile and the third quartile. So it's this distance divided by 2. So it's 8. Now we see the outliers that have little influence over the measure of variability in this data set. However, we also include only half or a quarter of the scores in the data set. A preferred measure of variability is variance because it includes all the scores in a data set. To define variance, we have to start from deviation. Suppose we have a data set of 3 scores, 2, 3, and 10. The mean is 5. Deviation is the difference of each score from the mean. So the deviation of score 3 from the mean 5 is minus 2. And the deviation of score 10 from the mean 5 is 5. If we sum up the 3 deviations, we'll get 0. And this is the 4th characteristic of mean from Chapter 3 of Central Tendency. It states that the sum of the differences of scores from the mean is 0. The sum of differences is the most straightforward way to measure variability, but 0 means there is no variability, which we know is not true. And the solution to obtain a value greater than 0 is to sum the squared distance, that is, the sum of squares. It gives us a minimal positive value, and later we can correct it by taking the square root. That will get us a standard deviation, and we'll talk about it in a couple of slides. So there are 2 ways to compute the sum of squares: definitional formula and a computational formula. If you have both the score and the population mean, or the score and the sample mean, you can use the definitional formula to compute the sum of squares. If you only have the score and the population size or the sample size, you can use the computational formula without calculating the mean first. Variance is the average squared distance that scores deviate from their mean. Population variance is represented by sigma squared and is computed by dividing the sum of squares by the population size. Its value can only be 0 or greater than 0 because the numerator is the sum of squares, which can only be 0 or larger than 0. Sample variance is denoted as S squared. The denominator in the calculation is the sample size minus 1. And we'll explain the next slide why it's not just the sample size. M minus 1 is the degrees of freedom for sample variance. We need to keep in mind that not all the degrees of freedom are equal to n minus 1. N minus 1 is specific to the degrees of freedom for sample variance. We just saw that to compute the sample variance, we used the sample size n-1 as the denominator. The sample variance we get is an unbiased estimator. If we use sample size n as the denominator, the sample variance that we get will be called a biased estimator. In order to understand an unbiased estimator, we need to learn about sampling distributions, which we'll have to wait until Chapter 6. So here we'll use an example to explain why it's better to use the degrees of freedom n-1 in the denominator. In this example, we have a population of 3 persons, A, B, and C. And the population size is 3. They each scored an 8, 5, and 2 in a quiz. And the mean is 5. The population mean is 5. We plug the numbers into the computational formula and get the population variance 6. Now I'm going to ask you some questions. We know that population variance is 6. If I draw samples from the population, is it possible that any sample variance is 6? It is, but the chance is very rare. Now another question. Is it fair to expect that the average of all the sample variances to be 6? The answer is yes. Therefore, if the mean sample variance is 6, it is the unbiased estimator of the population variance. If the mean sample variance is not 6, it's the biased estimator. We're going to use both n as the denominator and n-1 as the denominator, and see which one is the biased estimator and which one is the unbiased estimator. So now let's sample. We want a sample size of 2. So we take 2 subjects from the population each time. And we end up with a total of 9 samples. The sampling strategy we use is called sampling with replacement, which also has to wait until Chapter 6. The way we sample is that we take A out of the population and put it in spot 1. And then we put A back into the population and select another subject to put in spot B. And there are 3 possibilities to go in the spot B. We can select A again, or we can select B, or we can select C. So after we put A in the first spot, there are 3 possibilities. We can put A here, B here, or C here. So using this method, we end up with 9 samples in total. In the third column, we use a sample size n, which is 2, as the denominator to compute the sample variance for all 9 samples. And in column D, we use n-1, 2 minus 1 is 1, as the denominator to compute the sample variances for all the 9 samples. And at the bottom, we compute the mean of all the sample variances for column C and column D. And we see that column D, when we use the degrees of freedom for the sample variances, we get the mean variance is 6, which is the same as the population variance. So this is an unbiased estimator. So unbiased estimator is any sample statistic obtained from a randomly selected sample that equals the value of its respective population parameter on average. And in this case, we use the mean sample variance and get the number same as the population variance. The degrees of freedom for sample variance means if you know the mean, the value of all scores except 1, and you can predict the last score. We're using the same example from the previous slide. A, B, and C, except this time we don't know the score for C. And we still know the mean is 5 and the sample size is 3. We also know that the sum of differences, or the sum of deviations, is 0. So we can add up the deviations or the differences, and it's 0. And this way we can compute x is 2. We want to measure the variability, but cannot use the sum of deviations because its result is 0. So we compute the sum of squares. And now it's time to correct it by taking the square root of the variance, and we get a standard deviation. Standard deviation is represented by sigma for population and a lowercase s for the sample. Standard deviation is a unit to measure the distance that the scores deviate from their mean. The empirical rule for normal distributions with any mean and any variance, we can make the following 3 statements. 68% of the data lie within 1 standard deviation of the mean. So here is the mean, and that's 1 standard deviation to the left and 1 standard deviation to the right. And within 1 standard deviation of the mean lies 68% of the data. And then 95% of the data lie within 2 standard deviation of the mean. And 99.7% of the data lie within 3 standard deviation of the mean. For the blue distribution, the mean is 4. For the red distribution, the mean is 6. So the mean changes, but there are still normal distributions, so the empirical rule still applies. 68% of data lie within 1 standard deviation of the mean, 95% within 2 standard deviation, and 99.7% within 3 standard deviation. When the variance changes, the standard deviation changes, and the shape of the bell curve changes. For the blue distribution, the standard deviation is 1, and for the red distribution, the standard deviation is 0.5. So the blue distribution is more scattered than the red one. But there are still normal distribution, and the empirical rule still applies. 68% within 1 standard deviation, 95% within 2 standard deviation, and 99.7% within 3 standard deviation. This is an exercise to compute standard deviation. By looking at the table, do you know which formula to use to compute the variance? Now pause the video and work on it. When you resume the video, you can compare the results. In this exercise, we can use the computational formula. Here's the result. I hope you got it right. Now let's summarize the properties of standard deviation. Standard deviation is a measuring unit. A negative variability is meaningless, and from the calculation of square root, you know that it cannot be a negative value. Standard deviation is a numeric value. It's used to describe quantitative data. Standard deviation is the average distance that scores deviate from their mean, so it's always reported as the mean plus or minus standard deviation. The value for the standard deviation is affected by the value of all the scores in the distribution. So adding or subtracting the same constant to each score will not change the value of the standard deviation. but multiplying or dividing each score using the same constant will cause the standard deviation to change by that constant. Thank you for listening. Please let me know your questions and feedback.